In this talk, I'd like to introduce Flowtune, which is a resource allocation architecture for data center networks based on Flowlets, like George said. This is joint work with Balakrishnan and Devavrat Shah. So, everybody experiences this, right? You use the cloud, you think everything's fine, and then you get these high response times, and user experience is devastated. Response times directly influence the productivity of users on the cloud. For companies that sell products or display ads, it directly influences revenue. And for any organization, high response times can hurt the organization's reputation and its ability to retain users. In recent years, we've seen a trend among developers to break up applications in the data center into many small components or microservices. This has the great advantage that it is possible to now develop, deploy, and scale each of these microservices individually. But with these multitude of microservices distributed in the network becomes key to providing users with a good experience. So what can an operator do in order to control the behavior of their networks? Well, most of the mechanisms that operators have are packet-centric. So in switches, an operator can influence how packets are queued, for example, with priority queuing or weighted fair queuing, and how packets are marked and dropped, for example, with ECN, read, and caudal. On the servers, we have these mechanisms that control when the next packet is going to be sent, given per packet feedback from the network. For example, TCP congestion control adjusts congestion windows based on ACKs, duplicate ACKs, and latency measurements. These packet-centric mechanisms have three major disadvantages. So first and foremost, what application developers care about is their application-observed latency, and not per-packet latency. And it becomes very challenging to configure per-packet mechanisms to achieve application requirements. Second, because there are many nodes in the network and they have to communicate through the network in order for the allocation to converge, it frequently takes many round-trip times for these net allocations to converge. And lastly, if an operator wants to change how their network behaves, the operator might have to reconfigure all the components in the network, which is expensive. So in this work, we wanted to answer the following question. Can we design a resource allocation architecture where the operator specifies explicitly how they want the network to allocate resources, and then the network automatically, quickly, and consistently enforces this policy on network traffic? And ideally, it would be easy to deploy this in software. So our first observation is that packets are not the right granularity with which operators want to specify their network allocation policy, but rather flowlets are the right granularity. And here by flowlets, I want to overload the term flowlets with these application layer flowlets. So an application calls send with a buffer. That buffer's worth of packets is a flowlet in this work. And because application developers care about the network performance on these flowlets, it is very natural to both express policy and enforce policy using these flowlets. Design decision that we made was to centralize the allocator. And now because the allocator has enough information in order to allocate rates, it doesn't have to go through these multiple RTTs in the network. So this greatly reduces the dependence on the round-trip time for allocations to converge. Let me run through a quick example. Let's say Hadoop on server A has some data to send to B. First, A opens the TCP connection and starts transmitting. In parallel, A contacts the allocator and tells it Hadoop has some data for B. The allocator assigns rates, and in this case, tells A it can burst at line rate. So now A can stop slow start and just burst at line rate. Now say an ads server on C has some data for B. First, it opens the TCP connection, starts transmitting, and in parallel contacts the allocator and tells it ads on C has some data for B. The allocator reassigns rates according to policy, and now tells A to scale down to 1/8 of link capacity and C to ramp up to 7/8 of link capacity. To allow operators to specify policy, we adopt the Network Utility Maximization Framework, or NUM. NUM was developed in 1998 by Kelly and his colleagues. By the way, I'm going to use Flow and Flowlet interchangeably here. I'm going to mean Flowlet. In NUM, an operator specifies for each Flowlet flow a utility function. So on the x-axis is the rate allocated to the flow, and on the y-axis is the utility for any given allocation. So for example, a Hadoop big data Flowlet might have a lower utility function than an ads Flowlet, which generates immediate profit for the company. We solve NUM using the Lagrange multiplier method, which is an iterative optimizer, which essentially introduces a price for every link. Link prices are adjusted based on these two quantities, based on the difference between the aggregated flow rates on the link and the link capacity. You can think of the link capacity as supply and the aggregate flow rates as demand. So now when demand exceeds supply, prices increase. When demand is below supply, prices decrease. Given prices, flows choose their rates selfishly or locally. So each flow has its utility function, and it computes its price per unit bandwidth, which is the sum of prices over the links the flow traverses. By taking the utility and subtracting the price, the flowlet computes its profit, and each flow chooses its own rate in a way to maximize its own profit. And while every flowlet chooses its own rate locally or selfishly, it is the prices that drive the allocation to the global optimum. If we look at a single link, here on the x-axis is the link price, and on the y-axis is the aggregated flow rates that go through the link given the price. What the optimizer does is it adjusts prices until the aggregate rate is equal to link capacity. Now, if an optimizer adjusts prices using too small increments, then rates are going to very, very slowly converge to the optimum. On the other hand, if an optimizer uses too large increments, the rates are going to oscillate and never converge to the optimum. With Flowtune, we realized that because we know the explicit utility functions, we can compute how strongly flows are going to react to a change in prices. Or in other words, we can compute the slope of this function. And this allows us to run something like the Newton method and adjust prices with just right increments. We call this scheme the Newton exact diagonal method, or NED, and there are more subtle details in the paper. So NED allows our optimizer to converge with a smaller number of iterations than other alternatives, but we still weren't satisfied with this. Usually the way to run this iterative optimizers is set up all the inputs, then run iterations of the optimizer until the outputs converge, let's say 100 iterations, and only then output the result. But this is too slow. So let's say a new flowlet arrives into the system. Now it has to wait for at least 100 iterations before it gets allocated a rate. So what we wanted to do, what we tried to do, is keep prices between runs of the algorithm and run just one iteration at a time, then output the rates. So let's say you have a network, and let's say the prices have converged. Let's say this link's price is 1 cent. Now a new flowlet comes in. We run one iteration of the optimizer. Now the price is 5 cents. Then another iteration. Now the price is 9 cents. So as you can see, this has that advantage that a flowlet gets allocated a rate after even one iteration. But the rate it gets allocated is just not right. Because if you look at the prices here, 5 cents is too low if the network is going to converge to 9 cents. So flowlets through the too cheap link are going to send it over link capacity. And this is bad. This creates queuing and packet drops, which we wanted to avoid. So Flowtune adds a normalization step that scales down flows and ensures that the aggregate normalized flowlet rates are do not exceed link capacities. Let me show you how this works. Let's say the normalizer wants to normalize this flow. The normalizer computes for each link the ratio between the aggregate allocated rate and the link capacity. So here, 110%, for example, means that link is 10% allocated over its capacity. Then the normalizer scales each flow by 1 over the maximum ratio. So in this case, 1 over 110% for this flow. This ensures that there is no queuing and packet drops, and is able to achieve 99.7% of optimal throughput. So let's review the architecture. Endpoints send to the allocator notifications on when flowlets start and end. The allocator continuously runs iterations of the optimizer, and after every iteration copies the rates to the normalizer, which normalizes the rates, sends them on to the endpoints, which then enforce these rates. So given this architecture, we now set out to scale the system to large networks. So we wanted to build a multi-core algorithm. And we encounter a challenge that I'll illustrate through the following example. So here I've numbered the links 1 through 8. And let's say we have 2 cores. Core number 1 responsible for computing prices for links 1 through 4. And core number 2 for links 5 through 8. Now, each flowlet needs to compute its price per unit bandwidth using the sum of prices over the links it traverses. So for example, this flow has to sum up prices 4, 8, 7, and 2. This one, 4, 6, 5, and 1, and so on. And if you look on the right-hand side, you can see that the memory access pattern across cores is a random memory access pattern. Modern CPUs are highly optimized for sequential reads, but perform poorly on random access reads across cores. We're talking about 2 orders of magnitude slower when you run these algorithms. So the problem now becomes how to map work onto cores such that we can leverage sequential reads and minimize random access reads. And we believe that the solution I'm going to present is useful beyond num. So if you have a problem where you want to compute for every link in your network a quantity based on the flows that traverse the link, and a quantity for each flow using the links that the flow traverses, keep this in mind. So we have the network topology on the left-hand side. We arrange our cores into an n by n matrix and divide the network into n blocks. Here, n equals to 4. The core that is responsible for computing each flowlet state is chosen. The row is chosen by the source block, and the column is chosen by the destination block. Now, if you look at all the links going up from a block, let's say block 1, then all the flows that traverse these links are in the first row. So we choose for every row a core to be responsible for these upward links. Similarly, for the downward links, all the flows that traverse these links are in a single column of the matrix. So for every column, we choose a core to handle these downward links. We have the main diagonal responsible for upward links, the secondary diagonal responsible for the downward links. And in the paper, you can read the details on how we move from flowlet computations on the entire matrix to link computations on the diagonals and back using sequential reads. Using this multi-core architecture, we were able to schedule 4,600 servers on 64 cores in under 31 microseconds. So while we understand that this doesn't yet scale to the world's largest clusters, one thing to note is that of these 31 microseconds, more than half was spent in communication between cores. We had a system with these 8 CPU sockets, and communication across CPU sockets was very expensive. So we believe that with RDMA, it might be possible to scale this algorithm to many, many more cores, while perhaps lowering the communication cost in the algorithm. We deployed Flowtune on Amazon on EC2. We had 8 senders sending to 1 receiver, and we started a new sender every 50 milliseconds, then stopped the sender every 50 milliseconds. On the left, you can see how TCP cubic in Linux, Ubuntu 16.04, performs on Amazon. You can see that with 3 or more flows, TCP has a very hard time trying to converge to a Faro location, whereas Flowtune converges to a Faro location very quickly. We ran a similar experiment in NS2 with 5 senders. On the left-hand side, you can see how DC-TCP oscillates around the Faro location, whereas the second one to the left, you can see Flowtune converges to the Faro location within 1 averaging interval, which here was 100 microseconds. And note that with Flowtune, different flows can have different utility functions that DC-TCP doesn't support. pFabric doesn't share the bandwidth. It was designed to allocate all the resources to the shortest remaining time first. Stochastic fair queuing with Caudal had a lot of packet drops, so the application observed rates were very bursty. And XCP was very slow in reacting to changes in the network. We ran 3 workloads. The 3 workloads published in SIGCOMM 2015, the paper by Facebook, Inside the Social Networks Data Center Network. And we varied, on the x-axis, we varied the network load from 10% to 80%. And we measured on the y-axis the amount of allocation traffic from the allocator and to the allocator. You can see that even with 80% load and the most challenging workload, the system overhead was under 1.3%. But note that most networks are not 80% utilized. And in fact, that same Facebook paper claims that 99% of their rack links were under 10% utilized. So in that network, overhead would be less than 0.1%. There are several open questions with this network. I've told you that maybe an algorithm iteration is, let's say, 31 microseconds. What happens if you only have 10 or 20 or 30 packets? How do you handle these mice? One idea is to completely bypass the allocator for mice flows. Or perhaps use another scheme for the mice flows and use Flowtune only for the elephant flows and use maybe FastPass for mice flows. Another question is how to handle external traffic. A Flowtune cluster might have to communicate with other clusters or the internet. In the paper, we discuss a few ideas on how to do this, but an exciting opportunity that I wanted to mention is to have the servers measure the amount of external traffic and report it to the allocator. And then the allocator will adjust the link capacities to accommodate the external traffic. Flowtune does not support deadlines or co-flow scheduling, which are useful abstractions. For that, it might be possible to allow the utility functions to change over time, thereby essentially creating a market where Flowlets bid for network capacity. We've specified the multicore algorithm for 2-tier class topologies. It will be interesting to see if this can be generalized to 3-tier class topologies, which are common, and maybe how to make these good algorithms for the wide area network. So I've talked about an architecture for resource allocation in networks where operators specify explicitly the policy they want from the network, and the network automatically enforces this policy. We believe that these types of explicit networks can help bridge the communication chasm between application developers and network engineers, and allow applications and developers more control over the performance they get from the network, thereby improving users' experience. So with that, thank you. I'm happy to take questions.
Hi, Ihsan Kasi from LUMS. So in the last few years, we've seen several resource allocation schemes focusing on packets to flowlets, to flows, to co-flows. What's the right granularity for resource allocation and why?
Well, I think if maybe kind of a hybrid of all of them, maybe co-flowlets might be the right granularity. It is a useful abstraction, co-flows, and many systems are built that in a way that co-flows are a natural occurrence of the system that application developers want to reason about. So definitely that. But I think the Flowlet abstraction where you reason about kind of the application developers specify how they want their kind of application level reads to behave is useful.
Arjun Roy, UC San Diego. So you mentioned that you have a controller that seems to be logically centralized that performs these allocations, and that at some point maybe you have scaling issues based on how big your network gets. Is there any thought to if you partition the network and had a controller that's responsible for just subsets of the network in terms of how many nodes, how many links it handles. So that's not going to be globally optimum, but I was wondering if there's any thought to how your method would fare if you had these smaller subset of the network. Each of them are, you optimize within each of them, but you don't have a globally optimal solution. How well would such a solution perform?
Yes. So first, you might be able to still scale the allocator to multiple machines and scale to bigger clusters by having these larger n by n matrices and communicate with RDMA across machines. That's one idea. If you have multiple clusters, so when you reach the limits of that approach of scaling a single allocator or a single cluster of allocators, I believe that either you can reason about cluster traffic being small, so maybe they're in different warehouses and there's limited connectivity, or you can treat the traffic from an external cluster, from another cluster as external. It's really hard to reason about a hybrid. It's a good idea. Maybe you can communicate aggregate kind of capacity requirements between clusters in order to scale the system among multiple Flowtune clusters.
Thank you.
Hi, Stuart Wagner, DARPA. I have two questions. Take your pick. One is, it seems like your allocator needs fairly detailed information about the link states and the network states. And so particularly if you're going to go between data centers over the internet, what happens when there's a link failure or a significant drop in congestion? Have you thought about that? How quickly? And where does it get that information that it knows something has changed? And the other is, have you thought about prioritization of flows? You're already thinking about deadlines, so this is a close cousin to that. So take your pick.
Yeah, I'll start with the link failure question. So in fact, what I glossed quickly on in this talk is that the allocator actually requires knowledge of the paths each flow takes if you want to take into account what is happening inside the core of the network. You can abstract it out if you only care, you want to treat the network as a big switch, and in fact, in many settings that is useful. For example, in the public cloud, you don't know what the architecture is in the core of the network. But if, in general, you will want to know the links, kind of which link each flow traverses. And kind of the approach we took in this work was to assume that we can find that out from an external system. So let's say if you run an SDN control that controls paths, then you can learn that from the SDN controller. If you have ECMP in your network, you might need to know the link state and the functions that the ECMP has. And Arjun Roy's talk tomorrow should discuss another approach of learning these paths from the network. When a link fails, yes, we assume that another system notifies us. Your second question, can you remind me?
How do you build prioritization into the NUM?
So prioritization, you can effectively implement hard prioritization choosing different functions that are so far away from each other that it's just not useful to kind of the rate that is going to be allocated for the low priority flow is just going to be negligible. So you keep that flow alive. You keep some acts flowing in the network for every flow. It's not strict prioritization, but it is kind of for all practices, practical purposes is a prioritization.
Okay, Rodrigo.
So Rodrigo from Brown University. Just out of curiosity, in your travels through the world talking to operators and applications developers, how feasible or practical do you think it is that people would know how to express utilities and like, or how would you sell this API to the end users?
It's a good question. I think in many settings, operators will if you have one organization that can reason about the relative importance of traffic, that organization can enforce that kind of internally inside a company. Another way to do this is to actually account for the utility each organization is getting from the network and ensure that each one gets their fair share of the network, and just trial and error. But you're right that I think it might be too much to ask for everybody to get the right utility functions on the first try. It might be an iterative process.
Thank you.
All right, let's thank Jonathan Perry. Thank you.